In this video, we're going to talk about the periodic table and introduce it, which is kind of our biggest document in chemistry. It's a big deal. So here's a bunch of periodic tables. You thought there was one, huh? There's not. There's a whole bunch of them. The periodic table is just a way of organizing information about elements. And there's a lot of scientists out there, and a lot of them have different opinions about what is really important and what's only kind of important. So if you're going to categorize and organize information about anything, if we all sat down with the same giant pile of information and tried to organize it in a way that made sense to us, that was easy to navigate, we would all come up with something different. And so all of these are pictures of periodic tables organized in the way that someone thinks is the best way to organize information. And so there's not really agreement there. I think that the ones on the outskirts are particularly colorful and beautiful and fun. I like the hexagon one the most because I kind of like hexagons. Although this one right here always reminds me of a board game with all the different kind of swirls. And this one just reminds me of Star Trek. So I kind of like that one too. It's a spirally Star Trek. But the one that we use in our class, and that is agreed upon within the chemistry community and scientific community, is the modern periodic table of the elements. And that is this one right here. This is the one we'll use in this class that you'll see everywhere else and that everyone agrees on, who, isn't extremely opinionated. So let's dive into what this one looks like a little bit more. There's a ton of information in here. Chemists love to take a large amount of information and condense it. So that way you can cram a lot of information in one spot, but you have to kind of unpack it to be able to use it. So here's our periodic table. And this is not exactly the way it looks like. These two rows right here are really in this space right here. And so our periodic table should have the shape really that looks like this really long thing, right? Where these are right here before we get into our transition metals. But that doesn't fit on an 8x11 piece of paper. And so we take that lanthanide and actinide series and we set it down below the rest of the periodic table. This has information that you can glean from it looking at its rows, which we call periods. So there we go. So a row is also referred to as a period. And a group is a column of the periodic table. Can't spell column. And so we'll go through some of the patterns that arise between elements in the same period and elements in the same column, or sorry, group. So within this, on each of these different, like here's helium right here. Each of these different squares represents an element. And within this periodic table, and most periodic tables, you'll see the same thing. You'll see the chemical symbol, which is an abbreviation for the chemical. So heliums kind of makes sense. It's like capital H with an E. Some of them don't make very much sense, like tungsten. Tungsten is, let's find it right here. It's a W, so you know. Potassium is a K, right? Doesn't really make any sense in terms of like what the abbreviation is versus what, in English at least, versus the name in English. But you'll always have this chemical symbol, and you'll always have the atomic number, usually in the upper left-hand corner. It might also be center or at the bottom. You will, this atomic number here tells you the number of protons that are in the element. You will also see this number that usually has decimal places unless it's a very large element down here. And this is not a fully updated one. We've got more elements out here. This is the atomic mass. So this is kind of the weighted average mass of a mole of this substance, or in grams, or an atom in atomic mass units. And then if you're lucky, you're looking at a periodic table that also has the name of the element underneath the symbol to make it easier to track. Sometimes those are actually on like a separate page from the rest of the periodic table, which is always frustrating. So some other components that we have are group numbers, and you might see them come in two different forms. So helium here at the right-hand side of the periodic table is either will be listed as group 18 or group 8A. Group 8A is my preferred one, where it's separating the elements into two categories. The main group elements, which are our first two groups and our last six, and then our transition metals, lanthanides, and actinides. And where those first two and last six are our A elements, and then these other ones are B. And I like this designation because it'll correspond with the number of valence electrons a little bit better. So let's look at a few differences between different things within the periodic table and start with elements. So elements are always going to be defined as by their number of protons. So any variation in the number of protons between atoms means you're looking at different elements. And that's always going to be tracked by the atomic number, which we abbreviate to Z. And it's either on the top, left, middle, typically, for any periodic table by the element. And so every single element, every single atom within an element will have that same number of protons within their nucleus. And if you change the atomic number, you change the number of protons and you change the element. In general, if we're looking at a neutral element that's not an atom that is not charged, right? And we'll talk about ions here next. Then that number of protons will equal the number of electrons. So if I have 3 protons, I would have a +3 charge within my nucleus, and that would be balanced out by 3 electrons with a total -3 charge, because each electron is a -1 charge. So really, if I combine these two charges within the same space, I would have a net charge of 0. And that's what we mean by neutral. Now, if we change the number of neutrons within the nucleus of an atom amongst several atoms that have the same number of protons, then we are looking at different isotopes. And so isotopes are going to be defined by the number of neutrons within an element. So isotopes of each other are always the same number of protons, and the thing that varies is just those neutron values. And so the way that we determine what those are is from the mass number for the element or the set of atoms we're looking at. Mass numbers are abbreviated as A instead of Z, and they're always equal to the number of protons, which is the same as the atomic number, plus the number of neutrons. And so the mass number is not on the periodic table. Every now and then you'll see a periodic table that has, we've got lithium-3 and it's like, I don't know, I forget the atomic mass. Every now and then you'll see one that has then a list of numbers underneath it that's like 2, 1, that are really tiny. And these are telling you, or sorry, it would be greater than 2 or 1. It would be like 6, 5. This would be the mass numbers. I've only seen this a few times. Typically though, you need to look at a periodic, or not even a periodic, but you'd have to look up information about the types of isotopes that naturally occur for any element, and that would give you different mass numbers. Well, that mass number, A, will be equal to the number of protons and neutrons. So to know that number of neutrons, you always need to subtract the atomic number from the mass number to determine how many neutrons are actually there. So we have isotope symbols that are different than our periodic table, and they look like this. And they're great because they give that mass number information if we're looking at just one isotope. And so here, this is chlorine-35. And you can see this written, especially in medical settings, as chlorine-35, which is always going to be the element symbol followed by the mass number. because you can look up the atomic number on the periodic table. So just knowing the element will give you the information you need to know what the atomic number is. So we can abbreviate it even more. So our mass number of 35 and our atomic number of 17. This means I have 17 protons, and that means I have 17 electrons since this isn't a charged particle. And to figure out the number of neutrons, I would take 35, subtract 17, that number of protons, for a total of 18. So in this case, I have more neutrons than protons in my atom. And that balance of protons to neutrons really contributes to atomic stability. And so we'll talk about what are the most stable arrangements of those neutrons to protons within an element in Chemistry 163, so towards the end of our year when we talk about nuclear chemistry. All right, my last distinction I want to talk about within the periodic table are ions. And so within an atom, if we vary, or set of atoms, if we vary the number of electrons, then we would be looking at different ions of an element. So as the number of electrons increases or decreases relative to the number of protons for an element, we have different charges or ions of the element. So usually if it's a neutral atom, then we have the same number of protons and electrons. But if it undergoes a chemical reaction or a process where it gains or loses, it becomes an ion. If it loses electrons, it becomes positively charged because there'll be more protons than electrons in the atom. And so it will have an overall charge that's positive. And we call these cations. And then if it gains electrons, there'll be an imbalance where there's more electrons than protons in the atom. And so it'll have an overall negative charge because there's more negatively charged particles than positively charged particles. And these we call anions. So cations are positive, they lose electrons. Anions are negatively charged, electrons were gained. And a lot of times when we talk about electrons and charge, it's counterintuitive from what we've learned in our math classes, right? We're going to gain electrons, but the charge is going to become more and more negative. And we really associate negative as losing something. When my bank account is negative, I have less money than zero. But by gaining electrons, I'm becoming a more negatively charged particle. So it's a little bit of a flip. Here's some of the most common ions. The ones that are shown here are the ions, are elements that only form one type of ion. The exception here is they've put hydrogen twice in two different locations. Hydrogen is typically H+, so it can lose its one electron. It can also gain an electron to have two electrons and be like helium. So it's usually one or the other. But the rest shown here have just one common charge that forms for the element. And over here, we've got our positively charged, and over here, we've got negatively charged ions. And everything else that doesn't have ion listed means that it really has more than one possible charge that it can typically form. And so there isn't like oxygen's always -1, 2, even though oxygen is sometimes, well, anyway. All right, give these problems a try and I will solve them in a following video.